Welcome to a new lesson on heat transfer. Today we continue our discussion of thermal radiation. We want to define a few quantities that help us in the study of radiation. So we define irradiation, usually indicated by the letter G, capital G. That's a thermal radiation that arrives from the environment, for example, from other surfaces to the surface of interest. Part of this irradiation is absorbed by the surface and part of it is reflected back to the environment. Then we have the emitter radiation indicated by the letter capital E, and that's the radiation that's emitted by the surface by the thermal vibration of the particles on the surface. The sum of the reflector radiation coming from irradiation and the emitter radiation E is called radiosity, as indicated by the letter capital J. We also define a surface as opaque. Opaque is a surface that does not transmit light. So in this case, radiation can be definitely considered as a surface phenomenon, and materials that are opaque are metals, wood, and bricks. Other materials are instead semi-transparent. In this case, radiation penetrates through the surface, and so radiation in general cannot be considered a surface phenomenon. Glass and water are definitely semi-transparent materials, but they are opaque if the infrared portion of the electromagnetic spectrum is considered. So this means that materials behave in different way in different portion of the electromagnetic spectrum. Another very important quantity is the emissivity, indicated by the letter epsilon. The emissivity is defined as the ratio of radiation emitted at a given temperature T by the radiation emitted by a black body at the same surface temperature. So emissivity is a non-dimensional quantity and it's always included in the range between 0 and 1. So epsilon equal 1 indicates a black body, so it's an idealized case. In general, emissivity depends on the wavelength, depends on the surface temperature, but also depends on the orientation, so in the direction of emissivity, which is a direction along which radiation is emitted. So here we indicate the direction in three-dimensional space by two angles theta and phi. In most of the approximations, emissivity is considered only a function of the temperature. So we can write epsilon as a function of temperature as the ratio between the actual emitted power by the temperature, by the surface at that temperature, divided by the black body emitted power at that temperature, sigma t to the fourth power. So in the most general case, real surface, we said that epsilon depends on the wavelength lambda, on the temperature of the surface T, but also on the orientation. Instead, if we have a surface for which the emissivity does not depend on the orientation or the direction of radiation, then we talk about diffuse surface. We define instead a gray surface. It's a surface that has emissivity that only depends on the temperature. A further simplification is when we have a diffuse gray surface, so emissivity can be considered as a constant. So if we plot the emissivity of a real surface as a function of the wavelength, so epsilon is equal to 1 for a black body, so just a straight line in this graph. The dashed line here instead is the emissivity, smaller than 1 but constant, so it does not depend on lambda. So we have a gray surface. Instead, for the real surface, we have the emissivity that here in pink depends on the wavelength. So keeping this dependence of the emissivity as a function of lambda in mind, then the electromagnetic spectrum will behave in this way. So for a black body, we have a solid black line here. For a gray surface, we have a lower distribution by the same shape of the electromagnetic spectrum. Instead, we would have a more, let's say, ondulatory behavior and dependence of the spectrum on the wavelength in the case of a real surface. Other important quantities that help us in the study of thermal radiation are, for example, the absorptivity, and it's a ratio between the absorbed power of radiation coming from the environment divided by the incident total radiation. That's indicated by the Greek letter alpha, and instead we called reflectivity rho the ratio between the reflected radiation and the incident radiation. And finally, we call transmissivity the ratio between the transmitted radiation through the surface and the incident radiation. So all these quantities are non-dimensional, and each of them is included in this range between 0 and 1. We can represent these three quantities graphically. So we have the incident radiation, G, and we see that this thermal power coming from the environment, it's split in three parts. So we have rho G, that's reflected. We have alpha G, that's actually absorbed in the surface. And we can also have tau G, that's portion of the incident radiation that actually go through the surface and is transmitted somewhere else. Because of conservation of energy, we have that the sum of alpha, rho, and tau is equal to 1. We close our discussion today by mentioning Kirchhoff's law. In most surfaces, we have the emissivity equal to the absorptivity. This is really, really useful, and we'll see when we do exercises that this formula will really help to simplify the problem. Thank you very much, and I'll see you in the next lesson. Bye.